Molly Wakeling. I'm a PhD student at Cal currently at UC Berkeley. And I've been doing astrophotography for the last 5 years and was asked to come give a talk here. I've been going up to Blue Canyon the last couple months. I know Carrie Cleabord from the Astro-Imaging channel when he came and gave a talk on there once. I'm a panelist on that YouTube show. And he invited me up there, and I've gotten to know some members of the club that way. And it's been really nice to actually have a dark sky site to be able to go to, because the East Bay Astronomical Society, where I'm a member, doesn't have a dark site, but they do have some pretty cool telescopes up at the Chabot Observatory. Yes, I will share my screen and get rolling here. Astrophotography is my main thing. I occasionally do some visual observing at star parties while my astrophotography stuff is going. But really, I'm an astrophotographer. I've always been one to carry my camera around, and that's extended into this hobby now as well. Yeah, so a little bit of reasoning for you all why I should be allowed to give this talk, and that's so I'm getting my PhD in physics at Cal, and my bachelor's is in physics from Washington State. And I have accrued a lot of data over the last 5 years. I keep a spreadsheet with this info so that I can use it to refer back to or put data sets together that are similar and things like that. Adding it all up, I have about 92 unique deep sky objects that I've imaged, over 292 data sets, which consist of over 500 hours of data. And that's just the deep sky objects. I also have scientific data on variable stars, and starting to do some exoplanet observing as well. And also have quite a few data sets on the moon and planets and stuff like that. But those are usually pretty short. So I've just summed up my deep sky data here. The first part of this talk, I'm going to talk about gear. So I want to talk about what gear that I have, and then I'll go into some considerations for what gear you might want to get if you're interested in doing astrophotography. And then I'm going to run through some processing considerations. I'm going to look at basic processing first for complete astrophotography newbies, and then look at a little more advanced processing for people who've been into astrophotography for a bit in PixInsight. So yeah, so first, my gear. I finally live in a house, which is really nice. I'd lived in an apartment previously. And now I can set up in my backyard on I call it a semi-permanent, because I don't have like domes and stuff, but I can leave it set up back there because I have a nice secure backyard. So I actually have 3 rigs set up in my backyard, which is a lot of fun. This is my primary rig here on this slide. I have an 8-inch Schmidt-Cassegrain, which was my first telescope. I also have a Takahashi that I bought from my uncle at the family discount. That's been really awesome to have. I'm getting that set back up on another mount this weekend. I recently acquired a Paramount MyT, which has been a really awesome mount and an excellent upgrade from the Celestron mounts I've wrestled with previously. I have a ZWO monochrome camera. I have a Primaluce autofocuser. I use an off-axis guider on the 8-inch because of its long focal length, and it just works out better to use that with Schmidt-Cassegrains a lot of the time. QHY guide camera, electronic filter wheel. I really like my Astronomical CLS TCD light pollution filter, which is really necessary out here in the Bay Area where there's a lot of light pollution. I live just north of Berkeley in the town of El Cerrito, and I can see a fair number of constellations, but it's about Bortle 7. And I recently acquired some narrowband filters from Chroma, which I've been really excited to use and looking forward to applying to all those excellent wintertime targets. My second setup is what I call my wide field rig. So this is I just use like a Nikon 55 to 200 millimeter camera lens. It's one of the better lenses that I own. People have given me some. I had some previously before I got into astrophotography, And for like a stock lens, it's actually not bad. I'm working on saving up for a fancier camera lens, but that's still coming. I have a color ZWO camera I put on there, and another Astronomical CLS CCD filter, and a guide scope, and another guide camera. And this is on, I forgot to put the mount on there. This is on my Celestron Advanced VX, which is a really lightweight, compact mount from Celestron. And since it's from Celestron, it has a lot of problems. But with you know, a wide enough field of view, like using a refractor on it, it actually works fairly decently. This weekend, I'm swapping out the camera lens to put the Takahashi back on it for getting those big, juicy wintertime nebula coming up. And finally, I have the science rig. This is one I've compiled of semi-broken and random equipment people have given me. I'm actually giving a talk on this rig tomorrow for the American Association of Variable Star Observers, which I could put the link for to sign up for that talk if anybody is interested in learning more about that. But this is on a Vixen 8-inch f4 Newtonian that a member of my last astronomy club gave me, on a Celestron CGE Pro mount that is semi-broken but works well enough if I'm not doing long exposure astrophotography. A kind of crappy Orion Starshoot Deep Space Monochrome Imager 2. This is a CCD camera. It's slow, it drops frames sometimes, and it's just a cheap camera, but for doing variable star observing, you don't need high-end equipment. Automatic focuser, automatic filter wheel, and a set of photometric filters that were also given to me by a previous club member. So I have a lot of gear. A lot of it has been given to me or sold to me for a discount over the years. It's been really awesome. But it's allowed me to learn a lot about how astrophotography works with different kinds of gear and sort of all the ins and outs of how to just make stuff work by throwing odds and ends together, which as an experimental physicist is like my bread and butter. So my favorite thing to do is just to mess around with equipment and figure out how to make things work when they shouldn't, and it's a good time. Finally, when I travel somewhere but don't really want to take like a whole telescope mount, I throw that ZWO color camera and camera lens onto a Skywatcher Star Adventurer, and that thing all fits into a backpack, and I can take that with me on airplanes or just when I don't feel like packing a whole telescope or the weather is going to be dicey or something. This is the rig I brought to Chile for the solar eclipse last year with the DSLR camera instead to do a bunch of stuff down there. It's just really easy to pack up. Okay, so you can't have an astrophotography talk without showing off some of your astrophotos, right? So I'm going to show off some of my favorites. This is the Heart Nebula. This I actually captured from my backyard here in the Bay. I was able to get that nice contrast by using a hydrogen alpha filter. This is before I got the nice hydrogen alpha filter. I was using a 12 nanometer wide one that my uncle gave me. So I could do even better with the newer filter, but I'm quite pleased at how this one came out. This is an object I've been dying to image for years, and finally had good enough equipment and enough astrophotography knowledge to be able to image it. And I got to do it from a light fluted location, and it came out okay. So that was exciting. The Pleiades Nebula, or Pleiades cluster, with that gorgeous dusty nebulosity in there. This was also from my backyard here in California. I have these two up here to show that with practice and diligence, you can image in heavy light pollution of cities and get some pretty cool looking images despite those challenges. And this is also on my Takahashi telescope, but you know, a lot of it takes like processing and practice to get good images, but it can be done with diligence and practice. This was my first good astrophoto, as I like to call it. This was in my second year of doing astrophotography, and this is the Rosette Nebula. I wouldn't process it the same way now. It's I put a little bit more. I had to bump up the red quite a lot because this is actually done with a DSLR. So I have all this fancy equipment now, but I didn't always have all the fancy stuff. And this was actually done with a unmodified DSLR from a Bortle 5-ish location. And I'm still very, very proud of this one. This is my first like good astrophoto, and it always holds a special place in my heart. This one is a recent one as well. I had the incredible opportunity to go to Chile last summer and image the solar eclipse, but I also got to spend a week out in the Atacama Desert. And I've been trying to image Rho Ophiuchi for a couple years now. And I was at the Texas Star Party and was trying to image it. And I was taking like 10-minute subframes with a camera lens on my Celestron AVX mount and could just not get anywhere near the really cool images of this object that I saw. But this is a half-hour worth of exposures just at a really dark site with a really nice camera lens and a really nice camera. I got to borrow a Sony a7S modified camera and a Rokinon lens. And when you have good equipment, it can also really help your astrophotos as well. This is from the 2017 solar eclipse. I got to travel to Wyoming for that one. I was living in the Midwest at the time. Brought my DSLR out and a Borg refractor that I used to have that I passed on to my minion, another a college-age girl who I was mentoring astrophotography to. This is a composite of 10 exposures, and I was totally blown away with how perfect that my very first eclipse came out. That was really exciting. And then this is a wide field shot from the 2019 solar eclipse, again in Chile, with my older, crappier DSLR in stock lens. Oh yeah, and one more. This is what I currently have as my background. This is a 7-image mosaic from the Texas Star Party from above the upper field. If you haven't been to the Texas Star Party, I know it's quite a drive from here. Highly recommend going. It is amazing. And I was very sad that I didn't get to go this year, but you bet I will be there next year. I had a Vixen Polary star tracker, and I'm going to talk about these star trackers later on as well, that allow me to do these long exposure wide field tracked images and just get a really nice image of the Milky Way and the air glow in doing these 1-minute exposures from a really dark site. It's one of my favorites as well. Okay, so the first part of this section will be for how, like, if you're a visual observer and have no idea how to do astrophotography, there's actually quite a bit you can do with just a DSLR and a tripod if you just kind of want to get your feet wet and take some cool pictures. And DSLRs are easy to come by. A lot of people might have them already. And they're great because they're dual use. You can use them for regular daytime photography as well. So it's not just like an astro only thing. So people have stingy spouses, it can be a little bit of an easier sell. If you can do star trails, like the top left image there. That's really easy to do. Plop the camera on a tripod and take pictures back to back for a couple of hours, and you can get the cool like wheel of the sky effect. The top right picture is just using a fast, actually a cheap fast Nikon camera lens, an f2 lens. When I stayed up until 4 in the morning to get the Milky Way to be in the right spot for this shot when I was in Chile. This is probably one of the more epic selfies I've ever taken, standing with this 27-inch Dobsonian up there, which was awesome to look through, by the way. So you can just do some cool nightscape stuff, and you can even do some deep sky object stuff without any tracking equipment at all. The bottom picture is the easily recognizable Orion constellation. And I had this is like at 50 millimeters, if I recall, just using like one of the stock camera lenses, 50 to 200 millimeter, and just taking short enough exposures to not have the star streak, which was about 6 seconds at the focal length I was at. And I just kind of moved the tripod every 20 minutes or so back onto the target and let Deep Sky Stacker do the rest in mosaic mode. And it aligned all the frames. And I got this reasonable image of the Orion constellation without any tracking equipment at all. And you can see the M42, you can see the Flame Nebula. If I were to blow up this image and zoom in, you can actually see the horse head. And yeah, so you can even do deep sky stuff without any tracking equipment. If you have a DSLR and you just kind of want to get your feet wet and don't necessarily want to buy expensive equipment, there are these really cool mounts, these little star trackers, and you can plop your DSLR and like a long camera lens on there or even a short one and pack it up. It fits easily in any gear bags you have and set it up wherever and be able to do tracked exposures. It's not, you know, you're not taking necessarily 10-minute long exposures at super long focal lengths with these things, but you can get some really nice wide field shots or kind of medium exposure length or medium focal length type stuff. In fact, the one on the far right, that Omegon mini track, it is not powered at all. It's just a little clockwork that you wind up and it unwinds over the course of an hour. So if you want to go really simple, you don't need a computer to run any of these, and you can just get a little device called an intervalometer, plug it into the camera, and it tracks sidereally, and you're off and running on whatever target you want to image. So as an example of what can be done with those little star trackers, this is another image from Chile using that same really awesome Sony modified camera and Rokinon camera lens. This was on my Skywatcher Star Adventurer that I brought down with me. And this is Eta Carina on the left and the Running Chicken Nebula on the right, and a whole bunch of other deep sky objects in there, other nebula and globular clusters and open clusters and whatnot. And that's a series of 30-second exposures on the star tracker. Now, if you don't have quite as nice of a camera and lens, you can still do okay. So I have my ZWO color camera and a Nikon lens for this one. And this was up at Blue Canyon back in July. And you could tell I didn't quite get on target because you're doing this, you're sighting visually. There's no go-to capability on these things. But there's the Elephant Trunk Nebula. And if you can see my mouse, the actual elephant trunk is right there. It's kind of hard to see. But yeah, so it can be done, and you can do cool stuff with just a kind of more basic stripped down setup. All right, so if you already have some telescope equipment, you can use it. There are ideal setups for doing astrophotography, and there's also just using what you have to get started and to figure out whether you actually want to stick with it and then save up some money to invest in some nicer gear. This is my first telescope. This is the exact literal opposite of what you want in an astrophotography rig, at least to get started with. Schmidt-Cassegrain telescopes are really hard to do astrophotography with. I'll get into the details of that later on. This is an alt-az mount, which is also really not ideal for doing astrophotography. And this mount is not terribly stable either. It has some tracking issues. But for just kind of getting started, it really got me hooked. The two pictures on the right I was able to take with the setup with a DSLR screwed onto the back of that orange tube there, and got really compelling pictures of the Orion Nebula that just made me like want to cry every time I looked at them when I was first doing this. That Lagoon Nebula shot down there is my first deep sky stacked image. It's like 8 30-second images. And it was just so cool to be able to see more in the camera than I could see with my eye. And that was just a really cool moment. And then I could share them on Facebook and share it with all my friends, and they could see things that they, you know, a lot of people never get to look through a telescope. And it's kind of a way to be able to share that, because you can share Hubble images and that's cool, but it doesn't really feel real until it's you doing it or somebody that you know taking these images, and it kind of makes it feel more like it's real. There's sort of almost an unreality with Hubble images, which, I mean, you know they're real, but just doesn't feel the same as kind of experiencing it yourself, which everybody who's ever looked through a telescope can attest to. If you're looking to spend some money on putting a rig together, my recommendation is to start with a refractor. They are easier to set up and tear down. The wide field of view is very forgiving for tracking errors in lower end mounts. It's a lot easier to process photos and to get nice looking photos without having to do extensive processing. Definitely start with an equatorial mount. You can get a cheaper one to start with. I have a Celestron AVX. I wouldn't necessarily recommend it, but it is a mount that is less than $1,000. So, and I'm still doing stuff with it despite its problems. There are other cheap, lightweight astrophotography mounts out there, but the Celestron AVX works okay. Start with either a DSLR, especially if you want to be able to use it for multiple types of things, or a one-shot color camera. You'll ultimately want to get a monochrome camera. I'm going to talk about why in a bit, but having a one-shot color camera when you're just getting started is really helpful because the amount of work required to process those images is a lot less, and the amount of time it takes to get all the data that you need is also a lot less. So especially if you can't have like a permanent backyard setup and you get to pull gear in and out of the house every night, this is going to be the quickest way for you to get started in doing actual deep sky astrophotography is a lightweight rig and a one-shot color camera, like a DSLR or an astro color camera. So when you're evaluating what you want to use for doing your astrophotography, there's pros and cons to different kinds of telescopes. And I've put 3 types of telescopes on here. You notice that Dobsonians aren't here, and that's because the way that they're mounted, not being on tracking mounts generally, they're not really made at all for doing long exposure astrophotography. And there are nicer, there's like, you know, Dahl Kirkhams and Ritchie Creations and stuff, but I didn't mention those because that's like, if you're looking at those, you're already probably into astrophotography, so, and don't really need this talk. So refractors, like I mentioned, they're lighter weight. The fast focal ratio that they tend to be makes taking images a lot easier because you can get a lot more light in a shorter amount of time. Aperture is not king for photography. It is for visual observing, but cameras are so much more sensitive in the eye that aperture doesn't really rule the day for astrophotography. That fast focal ratio will help you out a lot more. So when I say fast focal ratio, I mean like f4, f5, as opposed to f10 of the stochastic grains. The bigger the number, if you're not familiar with photography, the bigger the number on the bottom of the focal ratio, the slower it is. And that basically means that it takes a longer exposure to collect the same amount of light. Refractors have tighter, nicer looking stars, a nice wide field of view, which makes it getting started a lot easier. However, because they're short, they don't have a lot of magnification, so it kind of limits the objects that you can image. You kind of have to stick to the bigger targets. They tend to have optical issues like chromatic aberration, unless you want to spend a couple $1,000s on your telescope and get a nice, well-corrected one. They can be long and heavy depending on which ones you get. Like if you get a 140 millimeter f7 behemoth, it can actually be heavier than a Schmidt-Cassegrain. And like I mentioned, the good ones are pretty pricey. Then there's Newtonians, which a lot of, there's a lot of Newtonian astrographs that are kind of designed for doing astrophotography. They're lighter weight. They tend to have fast focal ratios, but they also, like they have a fast focal ratio, but they also have a fair amount of focal length. So they kind of make a nice split the difference between lots of magnification and a nice wide field. It's kind of right in the middle. However, they're not without their own optical issues. You get a lot of coma, they need to be collimated a lot. They don't have a lot of back focus. So like if you're gonna have a filter wheel and a focuser and an off-axis guider and a bunch of stuff, you usually can't have all that gear on it because it's too far away from where the focus is. And they have diffraction spikes, which for some people like me are a pro. I think diffraction spikes look really pretty, but I think that's because the Hubble telescope has them and it just makes it look Hubble-like and pretty. But that can also introduce its own challenges. Schmidt-Cassegrains are generally cheaper you know, depending on how big, of course, that you go. They're really excellent for imaging the planets and the moon. So you can kind of do that in addition to doing deep sky. The optics are more easily correctable. I can put on one like $150 flat field corrector and get a pretty nice looking image. Not a whole lot of coma and really very little chromatic aberration. High magnification means you can go after all those little itty bitty targets, of which there are many: planetary nebula, galaxies, all kinds of stuff. Of course, you miss out on the larger targets because you can't really image the Andromeda Galaxy very well, or the Lagoon Nebula, or lots of the bigger targets. So, you know, pluses and minuses. They have a slow focal ratio, which means you have to use longer exposures to get the same amount of light, even though the aperture is bigger. The stars can be kind of mushy because of the secondary mirror making the light split around it. The stars aren't nearly as pinpoint as with refractors, and they're prone to mirror flop. That big primary mirror, the way that it's attached to the inside of the tube, it tends to flop around. It's not held in place like they are for Newtonians because of the way the focuser works. And that can cause a lot of problems with focus and precise alignment of your mount and stuff like that. So they all have their pluses and minuses. I have one of each of these. And definitely my favorite to image with is the Takahashi refractor, but I use measurement Cassegrain quite a lot for going after the tiny targets. Okay, DSLRs versus astro cameras. So DSLRs, I mentioned, are multi-purpose. You can see your image right away, which, especially if you're new at it, and especially if you're not super comfortable with using computers, can be a benefit. A lot of people are already familiar with how to operate a DSLR, and you don't need a computer to control it. You can use a little intervalometer to automate the exposures for you. However, because they're not cooled, they tend to be noisier. They have a spectrum filter that limits the amount of red light that gets through, and I'm gonna talk about that a little bit on the next slide. And not as many astrophotography acquisition programs. If you're gonna run an automated setup on your computer, a lot fewer of them support DSLRs. Astro cameras, like the ZWO ones that I have, they're typically cooled. There are uncooled ones that are cheaper, but if you're gonna get an astro camera, you may as well get a cooled one, which significantly reduces the background noise. They're specifically designed for astrophotography, so they don't have that spectrum filter in place that I'm gonna talk about. However, it adds extra complication, especially if you're new to the hobby, and it has to be controlled by a computer. You can't, there's no intervalometers for these. You have to plug it into your computer. So consumer cameras like cell phones and DSLRs have this spectrum filter in front of the camera sensor that it affects the transmission of the colors into the camera so that it more closely approximates how your eye would see it, which is, you know, especially for daytime photography, is what you want. When you take a picture of a tree, you want it to look as green on the camera as it does to your eye. And as you guys are certainly aware, because of all the red lights that we use at star parties, the human eye is less sensitive to red. So these spectrum filters drop off pretty significantly in the red region. Now, of course, hydrogen gas glows in the deep red. And when you're using a DSLR, then a lot of that light gets cut off. So you can't, it's a lot harder to get that light, and your images don't come out as well. You can get a spectrum modified DSLR and pay extra money, or you can get an astro camera that does not have that spectrum filter, as you can see on this chart here, the orange line, and be able to see a lot more of that red. And actually, astro cameras a lot of times don't have UV IR filters either, so you can actually extend out into the IR and do some cool stuff with imaging, like methane on Jupiter or Venus. I frequently use the IR filter to get sharper images on the planets and stuff like that. A comparison, this is not my image. I couldn't find a good fair comparison, but there's a guy on Cloudy Nights who made a fair comparison. This is the same exposure time and same night, I think, and the same optics. The one on the left is with a regular DSLR, and the one on the right is with the spectrum modified DSLR. So that spectrum filter has been removed, and you can see right away that you get much better color representation and a whole lot more hydrogen alpha, which is what makes astro images so cool, because there's so much hydrogen out there in the universe. So while you can use a DSLR, you will quickly want to move on to something else. I think I got my first astro camera about 2 years into the hobby, once I was able to save up for one. My ZWO camera runs about $1,000, so a little pricey, but worth it. Okay, so anybody who's kind of tuned in to doing astrophotography has inevitably heard of the CCD versus CMOS debate. They're both, the two sensor types were actually developed at about the same time, but CCDs kind of reigned supreme for decades. They're both kind of started being made in the 60s, but CCDs are used in laboratories and scientific imaging, and the amateur community was using film during that time because CCD chips were expensive. But with the advent of smartphones and the demand for consumer cameras, CMOS chip production had decreased in price significantly, and the quality of CMOS chips increased significantly. So that has come to dominate the market now because of smartphones largely. So some advantages of CCD chips is that they have a more linear response, which is not really as important for astrophotography as it is for doing science. And that linear response basically means that if you put in a light that is half as bright, then the light that the light that the chip detects will be half as much. Whereas opposed to like a CMOS chip, where that may not be the case. If you put in a light that's half as bright, it may be 60 or 70% of the total brightness scale on that chip. So it's not as scientific of a representation, but for astrophotography, that's less important than like for doing science. On CCD chips, you can do hardware binning, so you can combine multiple pixels together to create effectively larger pixels. The advantage of that is being able to collect more light in a shorter period of time when you're using a big, effectively big juicy pixel. You can't do this on CMOS cameras. Well, you can, but it's not really the same. You don't have as much of the benefit. CCD chips typically have lower dark noise and larger pixels. And larger pixels are actually better for astrophotography because that larger size means that they're collecting more light. However, they're slow. They read out very slowly. They have a lot of pixel defects and a lot of hot pixels a lot of the time. They're generally less sensitive than modern CMOS chips. This was not always the case, but in the last couple years has become the case. They have a lot higher read noise. Read noise is electronic noise introduced when the charge is read out from the sensor, and they're becoming obsolete. A lot of CCD chip manufacturers are no longer manufacturing them. CMOS cameras, on the other hand, read out really fast. You can do 100 frames per second on a planetary target, for example, which is really great for planetary imaging, which I'm not going to have time to get into tonight, but is another really cool use of astrophotography equipment. They're generally more sensitive. I did the head-to-head test on the same telescope with my CMOS camera versus a CCD camera that I was borrowing, and I could get a brighter image in 2 minutes on my CMOS camera than I could in 5 minutes on an equivalent CCD camera. And the CCD camera costs more. So hands down, I went with the CMOS camera. They have more pixels, which greater resolution can help in some cases. Of course, that doesn't mean that the pixels are smaller, which is actually kind of a negative against them. But CMOS manufacturers are starting to make cameras with bigger pixels as the demand is increasing. They do tend to have higher dark noise, so you actually want to take shorter exposures with these guys. And I already mentioned the hardware bending and the nonlinear response. I know it's a lot of techno babble with these topics, and I'm going to pause for questions here in a bit once I finish getting through the gear section. Another thing to consider with looking at camera gear and what you might want to use for your astrophotography is color, or one-shot color as we call it, versus monochrome cameras. So on a one-shot color camera, basically that's what your smartphone does. That's what your DSLR does. You take a picture, one picture, and you get all three colors, red, green, and blue. And it makes for faster data acquisition because you only have to take the one type of picture, and the processing is less complex. However, those cameras are less sensitive because basically you have what's called a Bayer matrix sitting on top of the camera sensor. And it's, as the picture shows, you have this pattern of red, green, green, blue. And those 4 pixels together make one color pixel. Now, the dye that they use for those color pixels, because they have to make it so small, these pixels are oftentimes only a few microns wide, a few millionths of a meter. The transmission is typically not very high, so you actually lose a lot of light going through that color filter. However, with a monochrome camera, you put a color filter in front of it, like a large filter in your filter wheel, and those things are very highly transmissive because they don't have to be extremely tiny. They can let through 99% of the light. So you can, so monochrome cameras tend to be a lot more sensitive than color cameras, even if the sensor is the exact same. You can also do narrowband imaging with monochrome cameras. And I'm not gonna have time to get into the details of that, but that's where you have like Hubble palette, hydrogen alpha, oxygen 3, stuff like that, which is really handy to do from light polluted locations. However, you need to take 4 times as much data. You got to take your red, your green, your blue, and it is really helpful to take luminance as well, which is all the colors, just using a luminance filter. The processing is a little more complex, and you have to have additional equipment. You got to have that filter wheel and the filters inside, which adds cost and complexity just by having more things that can go wrong. But the benefits of doing that can be pretty significant. So here's an example of what luminance, having a monochrome luminance channel, can do for you. This is the Eskimo Nebula taken from my backyard here in the bay. And the left-hand side is with my one-shot color camera. This is my Astro camera, my ZWO. And on the right side, I've added a luminance channel. So I took my monochrome camera, imaged the same thing, and put that as underneath of the color. And luminance, the eye is a lot more sensitive to changes in luminance than changes in chrominance, so you can actually get a lot sharper and clearer images with luminance. And also because you're getting all the colors through, you're getting more signal, it generally makes for better images. Here's another comparison of the Dumbbell Nebula. On the left is a monochrome camera using luminance, red, green, and blue as separate images put together. And on the right is my one-shot color camera. This is with, this is with 2 different telescopes. The one on the left is a telescope that had some chromatic aberration, so you can see the blue halos around the stars. On the right, I didn't have an IR filter on the camera at the time, so the stars are kind of bloated there too. So ignore the stars for the sake of this comparison, but you can kind of see what the differences are between the two. And in this case, I'd say that they're actually kind of similar to each other, but I couldn't find a better example of my data that had similar enough characteristics to be able to make a really fair comparison. But I have enjoyed processing my monochrome data a lot more than my color data. It's been a lot easier, despite the extra challenge of the extra time it takes. Okay, so the last bit of the gear talk is software. There's a lot of software out there. So I've included here ones that I've used and some ones that I'm familiar with that a lot of people in the community tend to use. in kind of 3 different categories: basic, medium, and advanced. In the basic category, you have your DSLR, and like you're using your telescope with a hand controller. You can go completely computerless and use an intervalometer with your DSLR. Those run about $30, no computer required. Or you can use some really cool DSLR camera control software called Backyard Nikon or Backyard EOS. That is really helpful for, you can set up a sequence to take like so many exposures at such different times with the Backyard Nikon and Backyard EOS software. That way I can set that up and then go do something else and not have to sit at my telescope the whole time. So that's a good starter pack. What I'm going to call the medium level, if you want to start controlling an astro camera, SharpCap is a piece of free software that can do some of that. Sequence Generator Lite is the free version of Sequence Generator Pro, and you can do a lot of, you can, with the Lite version, you can do like 1 target at a time, but it still allows you to do some automation. Or there's the SkyX, which costs money, but allows you to control your camera, control your focuser, control your telescope, and has a lot of other neat tools with it as well. On that same level is if you want to start controlling your mount remotely as well. So using the hand controller, you can use Sequence Generator Pro or Lite to program targets. You can say, I want you to slew to M31 from your computer, and it will slew there. And you can even have it take pictures from your camera and plate solve them and get your target centered. There's EQ mod, which a lot of people with Orion mounts use, and I'm not sure what all I think they use any mount that's ASCOM compatible. It's a piece of free software that you can use to control your telescope. You can also control your telescope using CARTS DCL or Stellarium or several other planetarium programs, which can be handy, especially if you're just doing like electronic assisted observing. And then finally, when you're starting to get comfortable with all the bits and pieces of astrophotography, you can move on to doing full automation. So in my backyard, I go outside, I set up my laptop, I pull the covers off my telescopes, I plug the USB ports in, I hit go, and I go to bed and they image all night. I have, several different targets programmed in. It slews to them, it centers them, it changes the filters, it focuses, it takes all the exposures, and then it does the same, moves on to the next target, it does meridian flips, it does all the things, and then it parks the telescope in the morning, and I wake up and I have a whole bunch of data on my computer from the night before, and I actually got to sleep, which is really great. It took a long time to get to that point where I could automate everything, but boy, is it nice to be able to sleep at night. I've had many, many nights of staying up all night, and yeah, sleep is great. One-time fee of $100 for that one. There's a new piece of software on the landscape called Nina, which is free and open source that does a lot of those same things. There's Voyager, which I haven't personally used, but there's going to be a presentation on it soon on the astro-imaging channel, so I'm interested to see that. MaxMDL has been kind of a mainstay in the field, but a lot of people are moving away from it because it's really expensive. And then there's ACP for if you have like a remote observatory out in the boondocks and want to set it up and not have to mess with it a whole lot, which is really expensive, but that's what a lot of like Deep Sky West and CR remote observatories and a lot of like the remote setups use because it has everything you could want. Yeah, okay. So that's some of the software that's out there. So before I move on to the processing component of the talk, I'll go ahead and take some questions on gear. I know I covered a lot of stuff in a short period of time with a lot of technobabble, but are there questions on the gear segment?
And for the record, all parties may now unmute themselves.
Or if there's questions in the chat that I can't currently see.
Have you used the Celestron autofocuser on your Cassegrain?
No, I got a focuser that plugs onto the telescope instead of using the focus knob, because I can get a lot more precise focus by moving the whole optical train in and out instead of twisting the knob. And the one I'm using right now is from Primo Lucha Lab. I know people who use ones that connect to the knob and spin, and so I guess that works all right, but I've heard better things about ones that don't use the knob and instead move your whole optics train in and out. So no, I haven't used the Celestron one.
Thank you.
So Molly, I take it the Sky X came with your Paramount MIT, right?
It did, yes.
I understand that's very powerful but very complicated software.
It is, yes.
Okay.
So I'm pretty handy with computers. I always have been. I worked in IT in college, and working with equipment and stuff is my favorite thing to do in science. And I will say the SkyX has been the hardest piece of software for me to learn, more complicated than PixInsight, and that's really saying something. The SkyX is weird. I think that they could use some serious design improvements, but it is powerful. I use it pretty much exclusively for the alignment model on my MIT, and for polar like fine polar alignment after I do some initial polar alignment. That's all I use it for. I don't use, it doesn't have a good sequencer, so like you can kind of sequence, but only one target at a time. Its autofocuser is good. I have used that before. I find Sequence Generator Pros to be just as good, so I just use that. And I can't invoke the autofocuser from Sequence Generator Pro, which is what I use for sequencing. So I don't use a whole lot of the features of the SkyX, but the mount modeling, the T-point, is probably worth all the money. It's really good stuff. And yeah, you have to control the MIT and the Paramounts from the SkyX. So I'll be paying for that software for a while.
Molly, do you have any experience with Sterizona on the Schmidt Cassegrains?
I don't. I have not tried. Are you referring to their Hyperstar?
Yeah, the F2.
Yeah. I haven't, just because they can be really finicky in getting the focus right and getting the focal plane set correctly. And honestly, I can probably do just as good with a lot of an easier time using a refractor instead. Because like I mentioned, aperture isn't really king for photography like it is for visual observing. And especially when you're at f2, you're kind of losing the goodness of all that aperture anyway, because your pixel scale is so small, or so large, I mean. So I haven't really tried it. I don't really plan to, because it's expensive and difficult, and I can get better images on my refractor probably. But I know some people who've done that. I know people who are using the RASAs and really enjoying them. So I think the opinions vary. Are there any other questions? Was there anything in the chat that I haven't seen?
I noticed in that other picture that shows you a modified DSLR, it had like 8 spikes on it.
Oh yeah. So first of all, the spikes are from the iris, the diaphragm inside of camera lenses. You don't get those with telescopes, but if you're using a camera lens, you do. I'm not sure if that's because they shot at a different focal ratio, like if they closed or opened the iris more, or if it's just because they were getting a lot more light, so it became a lot more obvious. But the poster who created that image said they used the same processing for both. So maybe it was just a brighter data set, or maybe they changed the focal ratio of their lens. I'm not sure. All right, well, if that's all the questions for the moment, I will go ahead and move on to the beginner processing section of this talk. All right, so if you're totally new to astrophotography, this section is for you. First of all, what is stacking? So when you take a single image, and I've got some examples of this in a bit, it's gonna kind of look like crap. It's gonna be noisy, it's gonna be hard to see your target, and you may not even really be able to see your target at all. What stacking does is what people who experimental scientists have been doing for forever, which is basically taking a lot of samples and putting it together into one set. So when you take more frames, so signal is coherent, so you're getting that light every frame, but noise is random, and that's going to change every frame. So when you take multiple frames and you average them together, then the coherent parts, the light of your target that's the same every frame, will kind of start to rise out from the noise. That's because it's random and it's going to vary frame to frame. It's not going to add the same way that the coherent light will. So, and you can see that in this example GIF here that a Reddit user posted from his rooftop in an unnamed city using a 6-inch Schmidt-Cassegrain and a DSLR at a stupidly high ISO. This GIF goes through, he has a single frame and then he stacks 4, 16, 64, 256, and 1024 frames. And you can see in the first frame, you can't even really see that there's a galaxy there besides the nucleus. But by the time you get to even just the 16 frame image, you can start to see that galaxy come out. And then by the time you get to 1000 frames, you have a relatively noiseless, he did no other processing on this, you have a relatively noiseless or low noise image, and that galaxy is very prominent. And what it's doing is using some basic Gaussian statistics, as we call it. So the more sample that your signal, the signal you want increases linearly with the number of frames that you have, but the noise increases as the square root of the number of frames. And so the ratio between those gets larger and larger the more frames you have. Now, if you know anything about what a square root graph looks like, you know that there's diminishing returns after a while. You can't just increase your SNR linearly forever. It will continue to increase, but less and less as time goes on. So in all practicality, you're not going to be stacking frames for your astrophotography. You're going to be stacking more like 20 to 100, depending on how much data you manage to take. But the key is that signal to noise ratio increase, where your signal increases linearly and your noise increases as the square root. So they kind of start to separate a bit, and your signal becomes a lot more prominent than your noise, and your noise can kind of disappear into the background, like this picture here. All right, so there's your science for the day. So to actually accomplish the stacking, you're going to take your light frames, as you might imagine. Light frames are the ones with your actual target in it on your telescope. You're also going to take some calibration frames. That's going to help with the noise reduction and with flat fielding your image. So the first type of calibration frame is a dark frame. And this helps reduce the noise from heat that it causes your sensor to trigger and from electronic noise. And I said that noise is random, and it is, so you're not like subtracting pixel by pixel the exact amount of noise that's in that frame. But if you average a lot of these dark frames together, you can kind of subtract an overall bias from your chip, kind of this lower noise floor, and at least reduce the amount of noise that appears in your background. And flats, what those are doing, for the darks, in order to take those, it's going to need to be the same exposure time as your lights. So if you have a 3-minute exposure on a galaxy, you need a 3-minute exposure on your darks. It needs to be approximately the same temperature, and it needs to be the same ISO or gain setting. So what I do with my DSLR is on nights when I'm not imaging, I check it out on the back porch, I plug it into my computer, and I use Backyard Nikon, or nowadays Sequence Generator Pro, to run a whole series of 30-second, 60-second, 120-second exposures as far out as I want. And I have a little thermometer that I throw out in the back porch with it. And then I collect a darks library over time of different temperatures and different exposure times that I use to calibrate my light frames. This is a lot easier with a cooled camera because you can set the temperature and you don't have to rely on the whims of Mother Nature. For flats, these are helpful for reducing vignetting. So especially if you're shooting something like a Schmidt-Cassegrain, the edges are kind of dark. This is a result of using a square chip in a circular aperture. And and also dust bunnies, which are inevitable. You can kind of reduce the effect of those dust bunnies. These need to be the same ISO and gain value, a white-ish background. So it's like people will sometimes put a white t-shirt over their telescopes during the daytime, or I've started doing twilight flats where I pointed at a blank patch of sky after sunset, but before dark. There's lots of methods to do this. And basically you're shooting for an exposure time that puts your histogram peak kind of in the middle. This is not a precise science, but roughly in the middle. And that's gonna get you a good enough exposure to be able to see those dust bunnies in that vignetting. And that will help reduce those unwanted effects. Okay, so I'm not gonna do a whole tutorial on Deep Sky Stacker because that would take up a lot more time than we have. But I'm just gonna I just wanna kind of demystify what that processing chain looks like and kind of give you a peek at what that processing would look like. And there's tutorials out there that go into a lot more detail on how exactly to do this. I have one on my own blog. But the quick run through is you're gonna import your lights, your darks, and your flats, and select some settings. There's a lot of settings to go through, and my tutorial gives some recommendations on what you should choose. Other tutorials will give you similar or different recommendations. There's YouTube videos, and basically you're choosing how you're going to stack these images, because you can just do a straight average, but you can do a lot better if you do things like pixel rejection. So if you have a satellite trail that goes through your image, you can actually reject that because it only happens in one frame. And statistically speaking, something that only happens once is obviously random and is not actually part of the deep sky object that you want to image. So you can use something like median kappa sigma clipping, and that will reject airplane trails and satellite trails and stuff like that. And then you hit the go button, and the stacking, it takes a while, especially if you don't have a really super fancy gaming computer like I have. And it churns through all the math for you. It aligns all of the images. It integrates all of your darks and all of your flats and calibrates your lights with those darks and flats. And after you go have a cup of coffee and eat some lunch and watch an episode of your favorite TV show, you can come back and you have a stacked image. Now, the result of this kind of stumps a lot of people at first, and I see a lot of posts about this on social media and the forums. Your image comes out and it's all like dark and monochrome and weird. And that's because it's in a linear state when it first comes out, and you have to do a little bit of tweaking to be able, that data is there, but it's buried in the fact that stuff in space is really dark. So you can make some simple adjustments in Deep Sky Stacker, and it's actually how I processed my images for about the first year or so of doing astrophotography. And you can adjust the location of the histogram. You can adjust the shape of this curve. You can adjust the saturation, a couple of tools there, and you can get your image to pop out from the background there. And you can get some reasonable results that way. But if you're willing to put out $10 a month for Photoshop, or if you're willing to put up with the weirdness of the free version of Photoshop called GIMP, you can do much more elaborate processing using Photoshop or GIMP. So if you save out that image without making any adjustments to it from Deep Sky Stacker, you can pull it into Photoshop and do similar things, but with a lot more control. So again, the image will be dark and really weird looking until you fix the colors and adjust the histogram. So as you can see in the histogram here, all the data is down here on the left side. This is the darks, the dark parts of your image, and all the data is there. And then this is the mid tones of your image and the highlights. So stretching is going to pull those histogram peaks a little to the right, and it's going to widen them. And that's how you're actually able to see your data. Right now it's very low contrast, and you're going to increase the contrast basically. And this is really mess with it until it looks good kind of approach. There's not an exact way I could say move the slider this much and then move it this much. It's kind of an iterative process. You do it a couple of times and keep tweaking that histogram until it looks reasonable. So I did that here, and you can see that it's a very blue image because I was using a light pollution filter that tends to make it look blue. But it's at a reasonable amount of brightness that I can see the target, and I'm gonna do more adjustments later. Now I need to balance the colors. In Photoshop, you can do this automatically, but it doesn't always take the correct guess because it just looks at the image and kind of guesses what it should be. You can do it yourself and make it look like you want. So still in the levels tool, you can adjust the individual channel histograms, the red, the green, and the blue, until you get them to mostly sit on top of each other, which will give you a relatively well color balanced image. And again, this is messing around. And finally, you take it over into curves, and that's where you're going to brighten up the image some more, adjust the saturation, adjust the color balance, mess around with it some more. Camera raw filter is also a really helpful tool for doing this because you can adjust the sliders for exposure and darks and midtones and highlights and all those things that if you are a daytime photographer are pretty familiar with. And you keep messing around with all those sliders until you get a reasonable looking image. There's still some color correction that needs to be done here, but it's now light enough for me to be able to see and work with and continue to tweak until I get something I like out the end. It's all very wishy-washy, really. And there's the camera raw editor. And finally, the last step is prettification. So doing those color adjustments, doing some denoising, and really great way to do that is if you put out 20 bucks for a set of tools called the Carboni tools. This is a set of actions that you can import into Photoshop, and it's just a one-time 20 bucks, and you can move it forward into new versions of Photoshop and different computers and stuff like that. And it has a whole bunch of automated tools to be able to do things like denoising and adjusting the shape of your stars, light pollution reduction, reducing gradients and flattening images, contrast enhancement, and a whole list that I've got over on the screen here that's probably too small text for you guys to see well. There's more details on that on the website if you just Google Carboni Astronomy tools, and you can go to that website. And I use these quite extensively back when I used to process in Photoshop. So I like to show off these pictures that kind of show the different stages, because especially if you're new to astrophotography and don't have the greatest amount of patience for things, you might look at that single frame of, you go try to image the Rosette Nebula or the Trifid or Rho Ophiuchi, and you look and you're like, this is garbage. I can't even see my target. I've got these really weird color hues. Like, why do I even bother? But then you have to remember that acquiring the data is only less than half the battle. Processing is more than half the battle. And as you step through processing them, whether you use Photoshop, Deep Sky Stacker, PixInsight, different ways of processing, you take it from being this weird, dim, color splotchy mess to an actual good astrophoto. All astrophotos are processed this way. You're not going to get like a single shot, really cool looking thing on the Rosette Nebula because they're just too dim and too far away. You have to stack them and process them and tweak them until you get a result that you like. And it really is different for each person. You'll see, for as many different astrophotographers as there are, you'll see a different representation of any given target. But I'd like to show these for comparison of why it's important to do processing and why it's important not to just try and take a picture and look at it and go, this is crap, and give up on the hobby. Because it really comes down to the processing at the end of the day. All right, so before I go into the next bit, which is sort of the, like, all right, so you've figured out how to take your data, you have done some stacking in Deep Sky Stacker, maybe you've done some processing in Photoshop, now you're ready to do the next thing, which is learn some actual good astrophotography processing software. Now, caveat, you can do a lot of this in Photoshop. if you're good with Photoshop, I know a lot of astrophotographers who only use Photoshop and don't use PixInsight and get excellent results. However, PixInsight is great, and I want to talk about all the cool things it can do. So before I move on to the PixInsight portion of this, are there any questions on basic stacking, deep sky stacker, post-processing in Photoshop, processing philosophy, stuff like that?
Have you tried the Maxim DL?
No, I haven't. It's expensive. It's expensive and it's expensive. Actually, a lot of people are kind of moving away from Maxim, I think, because of the other tools that do everything it does. The one benefit of Maxim is that it does your acquisition and your processing in one tool, which might appeal to some people who don't like to learn a lot of different types of software. But I personally have not used it.
What's the ratio on the darks and the flats and the lights?
Yeah, good question. So from a statistics standpoint, it's good to have a minimum of 20 frames for your darks and for your flats. I've started doing 100 frames for my darks and my flats now. Well, 50, I tend to do 50 for the flats, 100 for the darks if I can get them. Minimum of 20, but now that I can just throw it out on the back porch and set up a darks library, I try to get as many as I can. But for statistics purposes, at least 20. And it's not dependent on how many lights you have. That's just sort of in general.
I have a question.
Yeah.
On all this processing in a scientific way of looking at it,
Mm-hmm.
how can you calculate how much hydrogen or any other material is there if you're futzing with the chromatic effects of the picture? I mean, if it's too bright or too dim, I mean, how are you, because you just, isn't there a standard?
So that's a really good question, and a question that is often wrestled as one learns astrophotography and also debated hotly in forums all around the world. So scientifically speaking, that nebula you're looking at is emitting specific amounts of specific colors. It's going to have this amount of photons per second of this wavelength of red light. It's going to have this amount of photons per second of this wavelength of green light. But you are limited by what your camera can perceive. So that red filter, that green filter, that blue filter, they overlap each other a little bit. They have their response curves of what wavelengths they're sensitive to, at how much light they transmit at specific wavelengths. And then you've got your camera's response. How, if it receives 100 photons does that convert to 100 units of charge? And depending on the wavelength and depending on a number of other factors, that's not necessarily the case. So you have lots of things that are convolved in that, not to mention the effects of the atmosphere and what wavelengths get attenuated through the atmosphere, the local haze in your area, the optics on your telescope. There's a lot of uncertainties that get convolved into making it pretty much impossible to get a truly accurate measurement on what the flux of photons is at a particular wavelength, so that you can exactly set that wavelength in Photoshop, for example. So if you're doing wideband imaging, the red, the green, and the blue, it's really kind of a guess, because every camera is going to respond differently. Every telescope and every color filter is going to respond differently, and it's going to, it depends on the color spectrum of your monitor and the color spectrum of your eyes. Every person perceives those colors a little differently, and it depends on your processing philosophy. If you want to try and be as scientific as possible, there are ways to have a more scientific representation of the color scheme. I'm going to mention one of those tools in the PixInsight portion of this. But a lot of times you're just kind of looking at other pictures online, or if you know some things about your system, like I'm using the light pollution filter. I know it cuts out a lot of the yellow spectrum because of that's the spectrum of a lot of lights. So when I image galaxies, I have to fight to get them white balanced. But if it's a galaxy that's in the plane of the Milky Way, it is going to be more yellow because that light is being attenuated, being extincted, as we say in astronomy, by the gases and the dust of the plane of the Milky Way. So it's hard to say what the truth really is because there's so many complicating factors. When you're doing narrowband imaging, you can be a little more accurate because you're selecting a single wavelength, that hydrogen alpha wavelength, that oxygen 3 wavelength. But even then, you don't really set those colors exactly because it doesn't look nice. That's why you have the Hubble palette, where hydrogen alpha, which is really red, they assign it to be blue. And sulfur, which is red, is set to be red. And hydrogen is set to be green, oxygen is set to be blue, sulfur is set to be red. And those aren't their real colors exactly, because we see on this wider spectrum. So the answer to that question is beauty is in the eye of the beholder, more or less. And it's really hard to get that accurate scientific representation because of the limitations of the human eye, computer monitors, sensors, and everything else in between.
So it's all a lie. Just kidding.
It's all varying degrees of lying, yes.
It's an art form.
Yeah, astrophotography, I like to say it's kind of the nexus of science and art. There is some science to it because if you take a picture of the Orion Nebula and you make it all, and you assign it all to be shades of blue, for instance, those aren't really the colors it's emitting. But if you look through a telescope, it looks blue because your eye is more sensitive to those colors than red. So to the human eye, you're kind of seeing those blues, even though Orion omits tons of red because it has a lot of hydrogen. So there can be more inaccurate representations of it if you make it, if you totally mess with the colors and just kind of arbitrarily assign things and stuff like that. But it can also make really interesting, captivating looking images. The Hubble palette, like the famous pillars of creation, those colors are not even close to real, but there's scientific value in them because you can actually see where the hydrogen gas is, where the sulfur gas is, and where the oxygen gas is, where if you assigned them their true colors, you wouldn't be able to differentiate the hydrogen from the sulfur because they're both red and they're both very close to each other on the spectrum. So there's scientific data in presenting it in false color sometimes, or like the X-ray image of the fireworks galaxy that was shown at the beginning. Those are obviously false colors because we can't see X-ray. So it's not necessarily unscientific, but there's art involved in there with it just because you have to change something into a representation that the human eye can actually see, which if you look up in the night sky from Earth, we can't actually see these things. They're too dim. And if we flew by them in a spaceship, they would be really large and extended and we still wouldn't be able to see them very well. So it's kind of this mix between science and art. You don't want to be untruthful and say, these are the real colors when they're not. But you can be more truthful by having more accurate color representation to some degree.
Now, in the scientific community, do they assign a certain value to different colors so they all agree what hydrogen would look like or what sulfur would look like?
We don't really end up using color data really much at all for doing scientific observations. People who are going to study a galaxy, for instance, and look at the dynamics of that galaxy are going to take a monochrome image of it because they don't need the color. They just need to look at the shape. Or if you're going to look at where star formation regions are happening in a galaxy, you're going to take just the hydrogen alpha data and leave it monochrome because that's all you need. You don't need the color. So a lot of time that's not done in color, and it just gets shown on a plot somewhere as different concentrations. So those pretty pictures you pull out of Hubble, they are for PR purposes. The science that's done on Hubble, the pictures are much grosser looking.
Well, I was going to say, when you're asking for more money from Congress, you want to make the prettiest pictures you can so you can get that money.
Yeah, and honestly though, like the PR images that have come out of Hubble, those are the images that I looked at growing up and thought about the awe and wonder of what's out there, and kind of pulled me into science, you know, and there's the benefit of now you have another person doing science. So they even have their own scientific value, even if they're not providing any actual data, just by
Yeah, I don't
inspiring
want to
people.
denigrate the science part of it at all, you know, because it is valuable for that reason, because it brings people into the science of astronomy.
Yeah, or at least, you know, if they don't really ever get into it, kind of makes them aware that there's really cool stuff out there, and you know, there's a reason to explore space and understand these things, even if they don't have a, you know, they don't really want to get into science themselves, you know.
Right. So we're all pretty much Picasso's creating our own paintings of the universe.
Yeah,
It's
you
kind of
know,
cool in its own aspect. So
yeah, and being able to make an image that's captivating, that tells a story, as Adam Block likes to say, when you make an astro image, it should tell a story, it should say something about the target. Because you can have, you know, if you were to have a completely scientific representation of it, it wouldn't really look that captivating and cool, and you might not be able to actually see the things you want to see. But when I enhance the hydrogen alpha regions of that galaxy and you can see them, then, you know, you're learning about all the star birth, the crazy star birth that's happening in the fireworks galaxy, or the dynamics of two galaxies interacting, when you can actually see all the stars that are making a trail between the two galaxies in the Whirlpool galaxy. And then you kind of have a story of what's going on there when you bring out those dimmer features and bring them up to the same level of brightness as the bright target, even though they're actually 10 times dimmer.
yeah, there's definitely value in it. Cool.
All right, so I'm gonna move on then to PixInsight and talk about all of its super cool tools and why you should, if you get into astrophotography, brave the steep learning curve. So it is an extremely powerful post-processing software designed for astrophotography. Photoshop is not designed for astrophotography, but you can do a lot of stuff with it. It's a little pricey, but unlike Photoshop, it's a one-time price. There's no subscription, and you get all the upgrades forever. And there is a 45-day free trial, although 45 days isn't really enough to kind of get into it. As a pretty steep learning curve, but there's a whole lot of help out there. I personally use the Light Vortex astronomy tutorials very heavily. That's really influenced how I process my data. I have Warren Keller's book, Inside PixInsight. Rogelio Andreo, who has many NASA astronomy photos of the day, has recently released a book, Mastering PixInsight. Adam Block has a paid service for his tutorial videos. He also has some free ones, but I hear that they're really good. He's spoken on the Astro-Imaging channel a couple of times, and his talks, I got to see him at the Advanced Imaging Conference last November, and he's a very captivating speaker and does a really good job of explaining these things. And then of course there's all the forums out there, people asking questions and answering questions. Okay, so I'm gonna, just like with the Deep Sky Stacker, I'm gonna do a sample workflow, not going into a lot of detail. I'm happy to come back and do a more in-depth like processing workflow in Deep Sky Stacker and Photoshop, or in PixInsight, where I go through all these details. It could be like a workshop outside of a meeting or during a meeting or whatever, if people are interested in doing that, where I kind of do like a live demo. But I'm just going to run through a sample workflow just to kind of give you a glimpse of what the workflow looks like, just to kind of demystify what that looks like a little bit. Okay, so there's this really cool, pretty new tool to PixInsight, came out a couple months ago, called weighted batch preprocessing. That actually, like, I like to do all of the preprocessing bits separately, just so I have more granular control. But you can also just do them in one fell swoop and get pretty similar results using this script right here. And it does all the beginning work for you. So you plug in your darks, your flats, if you're using a CCD camera, your biases, and your light frames, and it calibrates your lights. It does hot and cold pixel correction. It debayers the one-shot color images, so it takes them from being raw monochrome copies of off the sensor to being a color image. It applies weights to the subframes based on goodness. So looks at the signal to noise ratio, looks at the star size and stuff, and you can apply some weights so that when you stack your photos, the good ones have higher priority. Registers your images, aligns your images. It can also stack, although you'll get a warning in PixInsight saying that it's better to do this step separately. And you can also combine multiple filters across multiple nights, multiple temperatures, if you using the add custom button and kind of taking some extra time to do that. You can actually have that done all at once so that you can set it and then go have your coffee, go have your lunch, go watch your favorite TV show and come back and you'll have either all of your pre-processed images ready to stack or your stacked image if you selected to do that. So this one tool kind of takes care of all the early steps before you get into the stretching and the prettification of your image. So my first favorite tool of PixInsight that really brought me over to it was this incredible tool called dynamic background extraction. And they're actually in the process of overhauling this tool and making it even more awesome right now. What it does is you sample the background of your image. So you take all these sample points, it generates sample points, and then you adjust them around to make sure they're not sitting on top of stars or on top of your target. And it takes a sampling of your background, does some complicated math, and there's some parameters you can adjust, and spits out an image with the background subtracted. This is really great for scenarios where you have light pollution. And I use it on all my data sets, even if they're taken under Bortle 1 or 2 skies, like this Eta Carina nebula, which was taken under Bortle 2, still had some effects from sky fog and whatnot. So you can see very clearly in this example, what it does is here's the stacked image before dynamic background extraction and after. And it also does some initial color correction as well, doing that background extraction. So really incredible tool, hands down, like worth the entire cost of the program for this one tool, in my opinion. So dynamic background extraction. There's also an automatic background extraction where you don't have to mess around with all the sample points, but I don't like the results I get from that as much usually. You can, so one of the cool things with PixInsight is, so in Photoshop, you pretty much have to stretch your image first, take it from that linear state to a non-linear state, where you're making it so that instead of the image being really dark and being kind of a more true representation of the actual data to something that you can actually see. In PixInsight, you can apply a screen transfer function that artificially brightens the way the image appears without actually changing the data of the image. So you can work on it before you actually stretch it. And there's a lot of stuff that is really useful to do before you stretch it that can actually get you better results at the end of your processing chain. So one of those is doing early denoising. So there's several different denoising algorithms in PixInsight. This is my favorite, multi-scale linear transform. The exact parameters I set here, I yanked directly off the Light Vortex Astronomy website and haven't really changed because they work really great. And you, so this is the initial image. This is a little segment of that Pleiades image I showed earlier. You apply a luminance mask over the top of it. And this is because a lot of the places where you see the noise in the image are the dimmer portions of the image. And those aren't the one, and there's less noise in the brighter portions. And so you actually want to protect the brighter portions because denoising will inevitably blur the image a bit. So if you put a mask over the top of it, you can denoise the noisy parts and leave the less noisy parts as they are and be able to hold on to a lot more of that fine detail in the image, like the fine filamentary structure of dust clouds of M45. And then after applying it, you can see that I still have maintained the sharpness of the dust there, but have strongly reduced the noise of the image. So another really cool thing, you can do this in Photoshop as well. You can make luminance masks and stuff. But yeah, a cool tool. You can do this before you stretch. My other very favorite tool of PixInsight is photometric color calibration. So when you're doing color calibration any other way, or in Photoshop, you're kind of taking a guess. You're aligning this the color peaks together and trying to make it look good. This is actually a lot more scientific of a process, this photometric color calibration, because what it does is it takes your image, you give it you tell it how big your pixels are, your focal length, and what object you're looking at, and it plate solves the image. So it looks at a database and knows what all the stars are. And it looks for a star in that image that is the same type as the sun, G2V. Our human eyes see sunlight as white because they evolved that way. So it uses that sun-like star as the white reference for your image and adjusts all the colors accordingly. So you get an actually pretty scientifically accurate representation of the colors. And that usually also looks good to the human eye because it's what our eyes, the color balance that our eyes are used to living here on Earth with our type of sun. And ignoring the messy background here in this image, this is an image of the Cocoon galaxy I took from here. And this is just the color channel. I haven't applied the luminance or hydrogen alpha enhancement and stuff like that yet in this image. But just the color data, you can see on the left, it looks pretty blue. And that's again, because I use the light pollution filter that gives it kind of a blue hue. And after photometric color calibration, this is a fairly white galaxy. And I've even already got the red of the star forming regions without having to do a whole lot of work. So it's my very other favorite tool of Fix and Save. Really cool color calibration. Another really cool tool is deconvolution. If you've ever done planetary imaging, you're familiar with this, where you apply a wavelet deconvolution, and this is doing the same thing. Basically, it's a lot of fancy math to sharpen an image and kind of pull out detail. Now you need to have a lot of frames in your data set to be able to do this effectively, or else you get really weird artifacts. But this is an example of the Eskimo Nebula taken from my backyard as well. This is just the luminance channel. And you can see the effect of before deconvolution and after. It's a bit of it's a multi-step process, but at the end of the day, you get a sharpened image that kind of brings back the detail that was lost by the waveriness of the atmosphere, which is really cool. Finally, after doing a bunch of linear state stuff, it's time to finally stretch your image and then apply prettification. So this is just showing the different stages of stretching. I forgot to mention this earlier. When you're stretching, you're pretty much only adjusting the midtones, so the grays, and you're going to move that to the left, and you're going to move your dark slider to the right in order to kind of kill the background and to stretch this histogram peak. And that's really why it's called stretching, because you're widening that histogram peak and increasing the contrast. So you can see how each of the steps have applied what that does to the histogram and what that does to the image. Finally, prettification. So after you have done all these other steps, you can combine your color and your luminance, adjust the curves just like you would in Photoshop, only in the curves tool, you can also adjust saturation, alpha, A, B, and C, and hue, which is really cool stuff for you. You can do high dynamic range transformations that can help level really bright areas with really dark areas of stuff, which is really useful for some types of targets, especially galaxies. Sharpening, you can make starless images, which if you've ever seen starless images of like some of the bigger nebulae, look super cool. Clone stamp out dust bunnies, dark structure enhancement. It's all the prettification stuff. And then other cool tools that you can use throughout the process. Some of these are before, you want to do before stretching, some you want to do after. There's a comet alignment tool, so you can use it to easily, if you have a comet image, align on just the comet and have the star streak, and that's a really helpful tool. Apply narrowband to enhance the colors of narrowband data in your wideband images. You can adjust saturation by hue. So if you want the blues to be more saturated, but nothing else, you can do that. This is really helpful for getting rid of halos, blue halos around stars. Multiple different stretching and denoising algorithms, combining multiple different exposure times, plate solving and annotating images, image analysis, all kinds of stuff. There's a lot of tools in PixInsight. There's a lot I still haven't used. Okay, almost at the end. I know this has been a rather long presentation. There's a lot of material to cover. This is kind of a comparison of the results I've gotten from different stages of learning how to process. So this is the same data set processed 3 different times. The first one was when I first took it back in 2017 and processed only using Deep Sky Stacker. The second one is I reprocessed it the following February when I learned how to use Photoshop to do some prettification. And then finally, I reprocessed it in July using all my new skills in PixInsight. And you can kind of see how the image and the quality of the image has evolved as I've gotten better at processing in general and using better software. So it's kind of a nice summary of my processing journey in one image. Okay, so to summarize all the stuff that I went over in this rather long talk, I talked about my gear, things to consider when looking for astrophotography gear, what is stacking, and then processing in different levels of software. But there's a whole lot more that I didn't cover in here. Astrophotography is a huge, wide-ranging topic. I did talk a bit about telescope control software, but didn't get into a whole lot of details. There's choosing filters. What kind of filters to use? What's out there? What is narrowband? There's planetary imaging. There's a lot more to say about nightscapes and image composition. There's eclipse imaging, which is its own beast. More ways to deal with noise, both in acquisition and in processing. And about scientific data taking. So I'm taking variable star data for the American Association of Variable Star Observers, for instance, or I'm taking I can view exoplanet transits from my backyard in California and submit transit data to NASA JPL's Exoplanet Watch project. And there's a lot to be said on how to do that as well. So with all that covered and a whole lot more to be covered in the future and a lot more to explore, are there any questions on any of that or the PixInsight stuff I just went over?
So you do like asteroid transition and all that?
Yes, so another type of scientific data taking that I haven't done is occultations, so asteroid occultations. And that requires some precise timing equipment that I haven't gotten around to getting. It's something I could do with the gear that I have, and I just haven't really gotten into it because you gotta have to be in the right place at the right time. And I like leaving my stuff set up in the backyard and don't necessarily want to go travel for an occultation. But a lot of people do that and submit really valuable data that is used to determine the shape of bodies in the asteroid belt and sometimes in the Kuiper belt as well.
Our club did something like that.
Oh yeah?
Yeah,
The East Bay Club uses an enormous telescope at the Chabot Observatory to do near-Earth object occultation measurements.
We worked with Paul Maley, who is retired from NASA, who spends a lot of his time doing occultations. He travels all over the world. Well, he got a hold of us a few years back and worked with us. We put a 12-person team together and captured asteroid Sappho occultation, and actually did very well. Our data came right in, and we got it published in the IOTA annals there. So that was really a great experience.
That's awesome.
To my knowledge, that's about the only real scientific endeavor we've tried. But like you say, it takes special timing equipment, and he brought that out.
Yeah. Yeah, and in fact, I think that's a lot of the first type of scientific imaging that people do, because you can also do it, it's more precise if you use a camera, but you can also do it visually. And you can also do visual variable star observations, and the AAVSO happily accepts those as well. But yeah, as far as scientific data taking goes, occultations is another big area that contributes really heavily to science, where you can use equipment that you already have in addition to getting a precise timing.
It's a real commitment, because we all spent 12 hours out there into the wee hours of the morning for, a 15-second capture.
Yeah. It's not easy, but certainly sounds really rewarding, especially because if you get to get published on something like that, it's extremely cool.
Yeah.
And you get that feeling of, I mean, that data is really important. Like, you know, it might be like, oh, cool, the thing is asteroid is crossing a star. What can we learn from that? But if you have multiple measurements across the length of the U.S. or any other part of the world, you can actually determine the shape of that asteroid. And we've determined that you can actually see that they're bilobed sometimes, or rotating, or all kinds of other stuff. So a lot of really valuable science to be done there, and the amateurs do a lot of that science.
Yeah, that particular one, it was tracked across the U.S. and had multiple timings, and so we did see a shape map. It was pretty cool.
Cool. That's really cool.
That's not your picture of M33, is it?
It is my picture of M33.
Oh,
but
wow. That's awesome.
with
That's really
caveats.
nice.
With caveats. This was done on a telescope at Deep Sky West. This was not done with my own equipment, but I processed it. I got some free.
Obviously, it has the diffraction spike, so it must be a mute, or.
It was a CDK, a Dahl Kirkham, a 14-inch plane wave Dahl Kirkham out in New Mexico with a FLI Kepler camera.
Wow.
I got some free telescope time from my buddy Tolga. He was testing some Astrodon filters and asked me to do a write-up since I do a lot of blogging and writing. So he gave me 5 hours of data time. I picked the target and what data I wanted, and then I did all the processing.
That's high-end gear right there.
Yeah, and that's where you can really see like I've not been able to get anything this good on my own gear, but I'm also in challenging light and atmospheric environments as well. But it shows you what's possible. You know, this is still amateur gear. It's expensive amateur gear, but it's still amateur gear, something that I could have someday. And actually, for those who aren't necessarily inclined to deal with the gear themselves, you can get a subscription essentially to Deep Sky West and other observatories where you share a telescope with other people, and you get the data is yours, and you process it, and you like pay a fee per year to get that data from those telescopes if you're more into processing than dealing with hardware. So that's something that a lot of people do as well. This is on a telescope that Tolga owns, although I think he switched it out for something else recently. But
He
yeah,
is a vendor,
it does
right?
show it's possible.
He is a vendor, right, Tolga?
He's a vendor. He has his own. He sells equipment, but he also does astrophotography in his own right. But yeah, Tolga's super cool dude, and he's also great to buy stuff from. I bought my Paramount from him actually.
Because he posts on cloudy nights. What's the name of his shop again?
Tolga Astro.
Okay.
Yeah, I met him on the astro-imaging channel when they invited me to stick around on the channel after giving a talk. And yeah, super knowledgeable and very helpful. Like, so I bought that Paramount and I was having some issues with it at the beginning, and I just got him on the phone and he helped me work through issues and I let him remote into my computer so he could see what was going on in the SkyX and stuff like that, and super willing to answer questions and super helpful.
Have you tried that easy deconvolution script in PixInsight, or do you just do it all the DVE and everything?
I do it all myself. When I do deconvolution, I create a point spread function using dynamic PSF. I create range mask and a star mask and do the pixel math to subtract the two from each other. I apply that mask, and then in the deconvolution settings, I monkey around with the settings. The whole process I learned from light vortex astronomy, so I didn't have to figure that out all on my own, because it is a little bit daunting, all the settings that are available. I don't know if they still have that script or not. If they have, I haven't tried it.
That I installed it the other night and tried it for the first time, and
Oh, so it's from a third party script.
a third-party script.
Oh, okay, yeah, I haven't tried it then. No, I'll have to check that out.
And it takes a while to crunch away, but it really saves a lot of work.
Yeah, this is because definitely like doing the deconvolution is probably the most time intensive step besides setting all the points in dynamic background extraction and waiting for the stacking to happen. It's the most hands-on because I have to select all the stars and stuff like that. So yeah, I'll have to check that out because it is a rather time-consuming process. Are there any other questions or somebody monitoring the chat?
I have not seen anything new on chat.
Okay.
I did send out a message on chat reminding everyone that you may now unmute yourself if you have a question.
Yeah, so I have a blog that I need to update with my most recent learning of stuff in PixInsight, but I have a blog where I have some tutorials on how to do at least some of the more basic processing because I haven't updated for the more advanced stuff yet. And also just, it's where I keep my log on my misadventures of dealing with celestron mounts and traveling and being out all night at the observatory and all kinds of stuff. I post most often on my Facebook Astronomy images. If you're interested in following that, it's kind of fun just to post it on my misadventures, post my latest photos. I'm eventually going to have an actual website someday.
Have you ever used astrophysics products?
Oh, yeah. Okay. So I almost bought an astrophysics mount instead of the MIT, but was convinced to get the MIT. It was cheaper than getting a Mach 2. But I hear nothing but good things about APs. I hear they're worth every penny. Nobody sells them because they keep them forever because they work so well and are real workhorses and last a long time. So I haven't used one myself, but I hear nothing but good things about them.
I looked through an AP Starfire 130. That was a sweet astrophysics 130 refractor.
Oh yeah, one of their telescopes. Yeah,
Sweet.
I haven't actually seen. I don't think I've actually seen one of their telescopes. I usually see their mounts. I don't think I've actually seen one of their telescopes. Yeah, I haven't looked through refractors very often. Usually when I'm at star parties, everybody's got their Dobsonians, and I love looking through Dobsonians. I got to look through Larry, what's his last name? Larry Knowles, something like that. There's a guy at the Texas Star Party that has a 36-inch Dobsonian that he sets up there. The mirror weighs 700 pounds, and he's got like a special hoist on the back of his truck. And it's so tall that if you're looking at anything at zenith, you have to go up to the top of this orchard ladder that he has set up there. But I got to look at M51 through it, and it looked like the picture. Like you could see, I couldn't see color, but I could see the band that connected M51 to NGC 59, whatever it is, next to it. Yeah, thank you. And it really looked like a monochrome, like one of my monochrome subframes. Like that's how bright it was under those dark skies up in zenith, or near zenith, with a 36-inch Dobsonian, and man, that was awesome.
Well, I don't have a question, but I sure want to compliment you on a great talk. You had it really well organized. You can tell you've been on the road giving this talk. That's a lot. I'm sure we're going to want to have you come back on some special topics.
Yeah, absolutely. And this is kind of an overview, a survey, if you will, of astrophotography. And there's a lot of stuff to deep dive into. And I'm happy to, I love to talk, as you can tell. So I'm happy to come back and talk more, especially with being over Zoom, making it so I don't have to make the drive out there. I can come out whenever I want.
But this is being recorded, right? Can we have access to the recording? I sort of missed it.
I don't know if the record button ever actually got hit, and I was going to
mention it. No, it is recording. It is recording.
It is? Okay, good. I was going to mention it at the beginning, and I forgot.
Can we have access to it? Because I sort of missed the first half.
After it's being edited by our Nicholas, our editor for this sort of thing, we'll make it available to members.
Thank you.
Yeah, I found this very interesting, and I want to thank you too, Molly, for your presentation.
Yeah, thank you.
Thank you, Molly, for
I would really
doing this.
enjoy doing these, and I hope that you got a little more insight into doing astrophotography, and it's becoming quite popular, and it's worth a try because it's you can take that experience of looking through the telescope and share a bit of that experience with everybody all over the world, especially when we can't share our eyepieces right now.
Yeah.
That's true. Yeah, very good talk, Molly. Very smart.
Thank you.
Well, then it's been 2.5 hours, so last.
Yeah, it was long. I'm sorry.
Not at all.
It was
Last
worth it.
call for questions.
I was going to say, where do I get my diploma?
I just wanted to say, Molly, you really beat the record here for the number of attendees too.
All
We're
right.
much higher than what we've had.
We have
So you
32.
got a reputation.
I don't think we ever had more than 26 before. But
Yeah, that was
we have
great.
32.
Really
Cool.
good.
Awesome.
Well, I'm going to say goodnight.
All right, good night.
Hey, Brian.
Really
If you
enjoyed
guys
it.
have
See you
any
next
other
time.
questions, you can hit
Good
me
night.
up on social media, or maybe I'll get my email address sent out, and I'm always happy to answer questions on particular topics and stuff like that.